related to physics. Looking
Yeah,
at moving human forms.
The setup that we use over there is identical to what they would use in motion pictures. The only thing is that we use 10 cameras. Because, I mean, between $4,000 and $5,000 a camera, we can only make some. Motion picture company, they can throw away money, so they'll put 100 or 200 cameras up on every axis. So it becomes much, much more stable.
My goodness. I think it's nice to wait right down to the wires. That way we get the maximum. Well, I think it's less than 1 minute left to go, so might as well start. I happen to know already Coach Schwab, and introducing today Jesse Rhodes, my friend, from the Department of Kinesiology and Public Health Education across the way from the building. And Jesse studies human motion. Kinesiology is a study of moving human form. And he has some pretty interesting techniques to do this. My interest in his work is that he uses an elaborate setup of cameras to actually keep track of objects moving in three-dimensional space. And so we'll hear something about this, I guess, and I think some of it will be historical. Jesse, I should say, got his master's degree from Indiana State University in Terre Haute in 2006, I believe it was, and his PhD from the University of Illinois in Urbana-Champaign in, I believe it was 2010. He's been here teaching in our department of kinesiology and public health education since so today's talk, as you can see the title up there, which didn't make it on the announcements, I'm sorry to say, is Fighting the Confines of the Laboratory for Real-World Applications. And I guess that's good enough.
Okay. Thank you very much. Okay, so I actually started out my career as a physical education teacher. So that's what my bachelor's was in. So why is a physical education teacher here to talk to physics and astrophysics professors? That should become pretty apparent in a little bit. But essentially, my research looks at human movement within the naturalistic environment. So basically out in the classroom. And what I'm going to show you is some of the techniques we use and how those techniques, while very, very accurate at this point, they tend to be a little bit constraining. They tend to have some issues as far as feasibility. So basically my main points, I'm going to talk to you a little bit about learning theory and constructivism, and then we're going to hit a lot of the historical context for both 2D kinematics as well as 3D kinematics, and then we're going to talk about this idea of optical flow analysis, and that's where a lot of motion capture is actually moving now. And then I have 5 current experiments that are utilizing these techniques, and I'm going to kind of go through those and lay those out. So hopefully we'll be able to fit that in within 45 minutes, and then we'll have some questions after that. Okay, so if we think about learning, there tends to be this idea within the ethos that learning is this teacher-learner dyad. The teacher is the holder of the knowledge, the learner receives the knowledge, and then the knowledge is either produced or imparted. Now, if you look at constructivism, we tend to think about it a little bit differently. We think of it more as learning is a triadic relationship between 3 constraints: the environment, the task, and then the learner. So these three constraints allow the learner to produce knowledge as opposed to receiving that knowledge. And if we look at it in a little bit more a focused version, we see the environment of the physical education student. They have three primary environmental constraints: the gymnasium they're in, their peer students, and then that teacher. And within this normal dyadic, a lot of the research falls within this. The teacher has a prescriptive task they give to the students, and then they give them feedback and instruction, and then the learner constructs that knowledge around that feedback on the tasks they're doing. My research diverts from this in that I look at the peer students as a key learner constraint. And we actually have quite a bit of literature out there that has shown this, what we call mimicry and or social coordination. That is, that people that tend to be in social situations that produce motor patterns will synchronize those actions and or mimic those actions between those. Also, we have a little bit of literature that says simply through the act of competition that they tend to change task constraints as well. So my research at this point is very interested in identification and quantification of mimicry between students within the physical education environment. And then eventually what we would like to do is create some type of instructional strategy that can harness that mimicry and actually try to use it as an underlying learning process within these students. Okay. So if we think of psychomotor learning, that's physical learning out in the gymnasium. It tends to be in the visual world. That learning is very apparent. We can see it, we can quantify it, and that's where motion capture comes in. Can we capture that motion, and then can we somehow compare those movement constructs between students? So I'm going to give you a brief history of some motion capture. This is Astro. Okay. That's a not so subtle reference to Hawking. Okay. So if we look at some motion capture stuff, by the way, physics people use a lot of bullets. I don't know. You guys have bullets that you use over here? Well, a lot of bullets. Okay. So this is obviously the same bullet. This is using strobe motion. Capturing it at a fairly high shutter speed, and we're going to talk about that here in a minute. Now, one of the first people to do a lot of major high-speed photography was Harold Edgerton, and he lived his life focused around shutter speeds and f-stops. How can you capture motion, and how can you make those pictures turn out very, very crisp? And obviously, there is a fight between getting very, very fast and how much light you need. Okay, bombarding something with light with a high shutter speed as opposed to not having enough light and getting very dim, very crisp pictures. And then the other thing I tell my students all the time, they're always like, oh, frame rate is so important, frame rate is so important. I'm like, frame rate is not that important. Frame rate's good, but if you don't have a high shutter speed, you just get a lot of blurry photos. So you want a high shutter speed, high frame rate, and then a lot of light. And Harold Edgerton did a lot of work with this, and we're going to see some of his work here. This is one of his. It's called The Death of a Light Bulb. It's 4 frames, and we can see the bullet coming in, impacting, and then blowing out. Here, we can see 3 bullets, 3 balloons, bullet through balloons. These pictures I really love because you can actually see the latex peeling from around the air. You can actually see the bullet here exiting, but you can see how the bullet has actually perforated the latex, and we have peeling around the air. And this is one of his more well-known, the cutting of the card. And this was actually at 1/1,000,000th of a second exposure time. Extraordinarily high. And of course, not only do you have to have the shutter speed that high, but you have to work out the physics of when is the bullet there and when can you capture it. So that becomes a much more in-depth thing. He also did this bullet piercing an apple. And overall, these just showed us that we can capture extraordinarily high movement or high velocity movement and make them very, very crisp. Now, when it comes to my field, what we want to do is we want to capture biological entities. And if we go back really quick, bullets, they tend to, it's really kind of neat, but it's one system. There isn't a lot of moving parts. The physics of it are fairly easy to work out. Okay? I don't want to minimize that they aren't that extremely easy, but when you bring in a biological entity, it tends to get a little bit more complicated. This is actually a problem that took us a long time to figure out. Why can a cat flip over? It has a lot to do with their tail, and there's some stuff going on there. This is actually one. I tried to get a peregrine falcon, but there are no peregrine falcon pictures out there. Has anybody ever seen any of the photos of a peregrine coming down on a bird? See the bird flying through the air and then a bunch of feathers. Just a bunch of feathers. Okay. Now, when it comes to biological movement, Edgar Murray, I definitely butchered his name, he was one of the first guys back in 1872. These 16 frames settled an argument about horse racing. The major argument in horse racing was that there was no flight phase. That at that time, if you ever saw a drawn horse or an image of a horse, they always had one leg on the ground because it was the wisdom at the time, oh, they obviously don't have a flight phase, they always have one leg of support. Well, he was actually, he actually got some grant money to go and look at this. And the side effect of this was that he developed some of the first motion capture techniques. And as you can see, he definitively put it to rest that the horse definitely does have a zero support phase, that they do have a flight phase. Now, this was actually put together from his 16 frames into a gift that was back in 2010. I thought it would be kind of neat to actually put the motion picture together. Now, what's interesting about this is this was 1872. This was much, much, much earlier in photography. Photography was in its infancy at this point. So being able to capture these, he actually had to set up 16 individual cameras. It wasn't like he could capture the same image on the same device. He had to capture on 16 individual cameras and then make those prints. What's really interesting about this is the negative of this print has been lost to history. We don't actually have that anymore. The only thing we have is